So here we're expected to expand this multiplication, and then we can rewrite this as a single power. So I have 3 to the power of 4, so it can be written as 3 times 3 times 3 times 3 times 3 to the power of 3, which is 3 times 3 times 3 times 3. It's all connected by multiplication, so that's very important that we check that. So it's all connected by multiplication, so I can just count up the multiplication. 1, 2, 3, 4, 5, 6, 7, 8. So it's going to be 3 to the power 8. Okay, so at any time we're unsure, we can just kind of expand and count up, because again, exponents count multiplication. So here we have 2 to the power 2, so it's 2 times 2. And this is 2 times 2 times 2 times 2 times 2 times 2 times 2. Well, really we could have maybe just done this. So we have 2 here. It's all connected. As long as it's connected by times, we can just count all the repeated multiplications. We've got 2 and 7. Instead of just saying counting this all individually, we could just count with the exponents. So I have 2 and 7. That's going to add up to a total of 9. Okay, so if I count 1, 2, 3, 4, 5, 6, 7, 8, not yet, that's definitely 9 there. Okay, so if we can start taking shortcuts, if you want to start taking shortcuts, you can, but just make sure you're really clear on what your counts are. So here's a fraction. We know that the top is times, the bottom is divide. So I have 5 times 5 times 5. Okay, on the bottom I have 5 times 5 times 5 times 5 times 5 times 5 times 5. Okay, so I have 7 on the bottom. I know that times and divide undo each other. They cancel out. And when we undo multiplication or division, we're always left with 1. Okay. So in this case, we have more division. So on the bottom, we can just count up the divide as 5 to the power of 4. In fact, since they work against each other, we can just subtract from each other and get 7 minus 3 to get the extra divisions on the bottom. So there are some shortcuts here, but if unsure, always just count, because exponents really just represent counting, multiplication, and division. So I'm going to let you guys do these ones on your own. Make sure you do these on your own. I'll do maybe the last one here. Here we just have to be careful because we want to make sure that we only count the 3's with each other and count the 5's with each other. So here I'm just going to expand this out just because this is kind of a little bit trickier. But I've got my 5's here, and I'm going to write my 5's with my 5's, my divide by 5's. Okay, and then I have my 3's as well, so 3 times 3 on top. On the bottom I have 3 times 3 times 3 times 3. Okay, and I also know that my times and divide undo each other. So I know I can cancel those out. I can cancel these times and divides out. And in the end, I'm just left with, well, it looks like I have 5 times 5 on top, 2 5's on top, 2 3's as divide, so I can count up my divide in the denominator like that. Okay, so again, work on these on your own. Make sure that you're able to do these on your own. When we talk about powers of 10 again are just either multiplying or dividing by 10. And if we multiply or divide by 10, we're just going to end up moving the decimal point over one position. But we don't need to have a reference. So we can use a reference as 1. So 10 to the power of 1 is going to be just 10. We just have 1 10. If we have 10 times 10, we end up with 100. Okay? And as we increase the exponent, I'm just multiplying by 10. So every time I multiply by 10, I'm just going to add one more 0. So 1,000 times another 10 is 10,000, times another 10 is 100,000, times another 10, so 10 to the power 6 is going to be 1 million, or 6 zeros, etc. So this is 10 million. Every time we multiply by 10, we can just add another 0. And same thing if we go the other way. If we divide by 10, we take away a 0. Okay, or move one decimal place. So divide by 10, this power of negative 1 really means divide. 1 divided by 10 is 0.1. 1 divided by 10 twice, the same as dividing by 100, so we get 0.01. And so our negative exponents are counting division, and really we're just counting the number of spaces a decimal moves over then. The one that's kind of strange is 10 to the power 0. But if we think about it, if we're multiplying in this direction, timesing by 10, then we must be dividing by 10 in this direction. So 10 divided by 10 does give us 1. And that's taking away one multiplication. Dividing is taking away a multiplication. So that gets us to 0. So that does kind of make sense. We really should take a closer look at that later, but it does kind of make sense if we think about timesing is going up with your exponents, dividing is going down with your exponents. So when we have this, we can write these as powers of 10. Okay? So if I have 1,000 times 100, that's 10 to the power 3. So my 1,000 is 10 to the power 3. 100 is 10 to the power 2. Okay, maybe I'll just highlight that. So I got my 10 to the power 3 times 10 to the power 2. And that's going to give us 100,000, or 10 to the power 5. We can just add the exponents up. We can add the multiplying by 10s up. So here I have 10 to the power 2 times 10 to the power 5. Well, really that works out to be 10 to the power 7, which is 10 million. And we can, when we're doing the numbers bigger than 10, we're just counting the zeros. This becomes 10 to the negative 2 times 10 to the positive 4. Well, I have 2 divides, 4 multiplies, so I have an extra 2 multiplications. Well, 10 times 10 is 100. So we can do this powers of 10 like this, and this relates to something called scientific notation. Okay, so we can multiply really, really big numbers by sometimes just dealing with these powers in this way and using these power rules. So here we have 10 to the power 7 times 10 to the power 9, or sorry, 2, which is going to give me 10 to the power 9 on top. I've got 6 tens dividing, so that means I have an extra 3 tens being multiplied. I have 6 divides 9 times, that gives me an extra 3 multiplications. And then that would work out to be 1,000 with 3 zeros. Okay,